That's not unusual around here. Normally, oh, yeah, nothing. I started recording, nothing on the slide, on the screen yet. Is the green light flashing? Yeah. I see light coming from our projector. Okay, as I promised, I'm switching gears today, and I'm moving to a different processor, and I'm going to jump right in on the instruction set for assembly language. But before I get started, let me just kind of make some comments about programming in assembly language. Everybody's had a course in C, correct? Some of you remember something about your course in C, some of you don't. Is that a fair assessment, right? Well, if you thought C was bad, I hate to tell you this, you're going to be slowly disappointed in assembly language because it's even more cryptic and more difficult to work with, and much more difficult to do anything with. And assembly language is important in understanding how a microprocessor works. It's probably not the best language to use for real work other than when you're forced to do it under no other choice. Back in the early days of microprocessor, and before we had good C compilers for embedded systems, almost all embedded systems were written in assembly language. I did a lot of assembly language coding back in my early career. I did very little of it toward the end of my working time, and especially when I was doing consulting work on large projects, because it's not very well suited for a very large project. You write a lot of code to do very little, as we'll find out in the next few weeks, right there. The reason I'm switching gears is very simple. As I did the little demo last week, the boards we have to work with are the 8051 boards. They're inexpensive. They're about 40 ringgits for the entire development set, where an 8086 development set will run us probably somewhere in the neighborhood of about 2,000 ringgits. So, I mean, you look at 40 ringgits versus 2,000 ringgits for a development set. It's much easier to work with the 8051s, especially when we start adding hardware in, we can just destroy our boards very easily. I'd rather destroy a 40 ringgit board versus a 2,000 ringgit board. 40 ringgit boards, to be honest, I spent that much for dinner at least one day last weekend. I think it's not, it doesn't break the bank to work with that there. So we're going to look at the 8051, and in this, I'm not giving you a lot of background on the 8051. I'll cover some of that in these slides here. I'm jumping really to the six sets of slides out of this particular book to just kind of go over the instruction set that there. Yeah, that doesn't work, so we will. Okay. First off, we're going to look at the 8051, the architecture, and the memory organization. We went over the memory organization to a degree with the 8086. It's a completely different animal here. The way that this is, it's relatively confusing, so forget everything I talked to you about the 8086 for the next hour right there. We're going to get into the addressing modes. These are somewhat confusing as well. You're going to have to learn them. They will be on the final exam, by the way, along with giving examples of that there. And then we're going to go through all the instructions. We may not get through this whole set of slides in the next hour. We'll try, but we'll see. Not bad. It's good here. Yeah, there. Why is don't tell me my little slide projector there is not working. It doesn't appear to be working. Right there. It's a very old one. Right there. Oh, okay. All right. a computer instruction. Now, assembly language is what the microprocessor understands, right there. That is the language written for the microprocessor. Actually, what the microprocessor understands is machine language. When we look at our microprocessor, and here's our program memory, right there, and it starts off with address 0000. It goes all the way to FFFF. It's 60. We're looking at 64K of program memory, and we have instructions. Each one of these is 8 bits or 1 byte, and we have an instruction pointer that points to the instruction, the next instruction. The next instruction is an 8-bit or 8-bit byte that tells the microcontroller or processor what it's supposed to do next. Then followed by that, there might be some operands. Operands are what the it's supposed to be working with that there. So as we look at that there, so it's made up of an opcode. An opcode is the instruction itself, followed either by 0, 1, or 2 operands. That there. The opcode is the actual instruction to identifies the type of operation to be performed, and the operands identify the source and destination of the data, and it may contain the data itself. So not all instructions have operands. So some instructions have 1 operand, some have 2, some have none, right there. So the operand can be the data value itself, a CPU register, a memory location, or an I/O port. Right there. That's going to tell it that there. So the format is a little strange. It's the instruction followed by the destination and the source. The data moves from right to left. Yeah, right to left, right there. So when we look at an instruction, right there, so when we look at an instruction, it may be of the type move A, comma, B. What that essentially does is it takes the contents of register B and moves it to register A, right there. So the normal reader will look at this and say move A to B, but that's the opposite of what it's doing. It's moving B to A, right there. Move into A, whatever is in B, right there. So that's a relatively simple. This is a legit assembly language instruction right there. So before we can get into that, we're going to look a bit at the internal architecture of the 8051 right there. The 8051 contains an accumulator, which is often referred to as A. The accumulator is A. And then we have another register inside the processor called B, right there. Those are 2 registers right there. Then we have a couple of temp, which we don't ever access. The temps are internal to the processor. We don't ever get to that there. Then we've got our static RAM register right there, and it points to our static RAM. There's 256 bytes of RAM inside of our 8051. Now, the 8051 also has that there. It has our special function registers. We'll talk about those in more detail here. And it also has external memory. External memory. Memory right there. Now, this particular processor gets relatively confusing when we go to this next slide. The 8086 only has memory. When we talk about, depending on the processor, it can go from 0 to 1 gig, to 4 gig, to 24 gig, to so many petabytes, depending on how big the processor is. The 8051 has far less memory on it. Far, far less memory right there. Not very much at all. But it's got 3 different memory locations right there. You can look at it, this is 3 different condos, buildings right there. It's got the program memory, which is where your program resides. When you write an assembly language program, and you download it to the board, it's going to be downloaded into program memory, right there. So, and keep in mind that you will be asked, what are the three address spaces in the 8051? And I'm telling you what they are. One is program memory. The other is the internal data address space. Now, internally, this thing only has 256 bytes, of which we can't use much of. That's very, very restricted. This thing has very little internal memory as far as memory inside the processor. The original 8051, as introduced by Intel back in 1981 or whenever it was, 1982, only had 256 bytes. Out of that 256 bytes, 128 bytes are set aside for the special function registers. You cannot use them. The first group of locations, this is 32 bytes, and those are reserved for the registers. And we'll talk a little bit more about the registers. The 8051 has special registers called R0 through R7, and we can have more than one bank of registers. We can switch between the banks that's there. The advantage of using the special function registers for most of our coding is that they're easier to address. We just say R0, R1, R2, and we don't have to give it an address right there. And we can switch banks, and we have 32 bytes assigned. We have another 16 bytes. This is 16 bytes. These are general purpose registers that we can use for whatever we want, and they can be used either in bit addressable or byte addressable mode. In other words, we can look at bit, location 32 hex, bit 7, and set that bit or clear that bit. No, not 32, 22, for example. 32 is only byte addressable. So the only place we've got is between right here, 02 hex, or 020 hex, and 07F hex. That's all we've got to work with on our processor in terms of RAM. Not a lot of RAM. However, our processor has another 4K right here. This is 4K that's on the chip, but it's called external. So we've got 4K of external RAM on our chip that we can use it for whatever we want, but we have to treat it as external memory. The reason for this, and this is it's kind of confusing because we call it external data, but it's internal to the chip. So it's internal external memory right there. It's internal to the chip, but it's treated from the state of the programmer as being external. The original 8051, as developed by Intel, only had 256 bytes. This external data space that's built on the chip was not in the original chip. In order to keep things compatible with existing compilers and existing code, anybody that uses an 8051 that wants to put external RAM in there puts it in the external address space. So we've essentially got 4K plus another, 96 bytes available to us, roughly, is what we've got available to us in terms of that there. So we have to treat this differently with, whenever we want to do a move, we have to use the move X instruction right there. So there's a move instruction and then there's a move X instruction. If we do a move instruction, we're talking about the space up here. If we do a move X, we're talking the space down here. So there's two different sets of memory that they have to be treated differently. Program data share the same address space, but are accessed via different instruction types. That is completely different than when we looked at the 8086 had one big set of addresses right there, that went from 0, 0, 0, 0, 0 to F, 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 right there. Now we've got program 0, 0, 0, 0 to F, F, F. We've got internal, which goes from 0, 0 to F, F, which we can't use all of. And then we've got external, which goes from 0, 0, 0 to F, 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 F. Of some of which this is on the chip. This is not physically present right there. So here we've got three different memory locations, sets of memory locations. So you can have something in address 0, 0, 0, 0 in program memory, something completely different in location 0, 0 in the internal memory, and something completely different in 0, 0, 0, 0 in the external memory space. They're all address 0, but they point to three different locations, and the processor knows by the type of instruction you give it whether it's going to be code memory, whether it's going to be internal data memory, or if it's going to be external memory. The instruction tells the processor which one of these three to go to, right there. On the 8086, you just had one set of memory. That's it, right there. Now, the 8086 did have we did talk about it, we did have an extra set of memory here for I/O. We didn't talk about that. So the 8086 did have a separate memory space for I/O, but we did not talk about that there. This one does not have an external memory space for I/O. The I/O actually is contained within the special function registers, right there. And we'll see that here in a minute. There. Okay. Right here is the internal data space. This is a little bit more detailed slide. And by the way, I'm not going through these slides because they have no value. These are very important slides. Because as we start writing assembly language instructions, we need to be aware of what these are right here. So, as we look at right here, we've got our register banks. This is 00 to 1F, right there. Those are the default registers. Those are the register banks. Memory location 00 is the same as R0 in bank 1, or bank 0, excuse me. Location 09 happens to be a R1 in bank 1, right there. See, these are the addresses right here. So 09 happens to be R1 over here in bank 1. And we have to keep track of what bank we're working with when we write our code. If we change banks, and then we want to go back and access something in bank 0, we got to change back to bank 0, right there. So we've got, and there's 8 registers, R0 through R7, in each one of those. And we call it R0 through R7, no matter which bank we're dealing with, but we have to change the bank number. There's another location right there. And then we've got, from location 30 to 7X is just general purpose RAM. Now 2F down to 20, these can also be used as general purpose RAM. They have the added advantage that we can also address the bit. So if I say set bit, that's an instruction, and I say 44, that's going to set this bit to a 1 in memory, right there. I'll blow that up a little bit so you can see that that's 44. Right there. So if I do a clear bit, 44, right there, that's going to clear that bit to 0. So we've got that there. But the fact that we say set bit or clear bit tells us that we're clearing a bit. So it knows look for an address in this location right here, right there, in that group there. So we've got so many bits that we can set and clear. And bits are very useful if we want to set flags, things like done, whatever. We can set bits for various purposes. That there. If we only need a 1 or a 0, right there. So now, this slide here is a critical slide, and I know you're having trouble staying awake through this stuff. You're struggling. So, if I pick on someone for dozing off, don't take it personally. I know this room is warm and it's right about lunchtime. Some of you are probably getting a little hungry at this point, right? It's not quite lunchtime, but we're getting there. Okay, the special function registers are a series of registers that are used to control the processor, right there. Now, in these special function registers, we're going to find things such as P0, P1, and P2. Those are our ports, 1, 0, 1, and 2. We have 2.5 ports available to us on our processor. You also see port 3 there. We're not using port 3 on our processor. It's not on our processor. It's on the one discussed in these slides, but it's not on ours. And then you also find, for example, that there's going to be port 5, port 4, port 6, port 7. Those are also not on our processor, right there. These here, in this column here, those are all bit addressable. So I could do a set bit P1.1. That sets the bit for P1.1. It puts a 1 on port 1, which happens to be a pin, output pin on our 8051, and we'll set that high. So I could very easily set that high. I can also read a port and see whether it's high or low, right there. So I could do a jump, jump no bit or whatever, and we'll get in those instructions up there, and do a jump command looking at a particular, to see whether a pin is high or low. I'm looking for a push button, a button to be pushed or not. So I can look at individual pins on my ports very easily with this particular processor. Incidentally, this is one of the differences between a microcontroller and a microprocessor is microprocessors generally are not easily used for doing bit addressable things like that. They don't normally have bit addressables. So for control applications, processors are pretty much worthless. You can do it, but you got to write a lot of additional code. Microcontrollers are designed for doing embedded systems and control operations. That's what these are designed for. General purpose processors are designed for computing. So when we look at that, we'll also see a lot of things in here, such as here's our timer control. Timer, our low registers, our high registers. These are not the high low. These are the high and low registers for timer 3. Our timers are there. We've got our port 1 mode where we set up our how we set up our port, whether we want it to be an input or output, whether we want it to be disabled or enabled. We've also got things such as the crossbar, which that's a port that's added on that there. We've got our serial buffer where we can do serial communications. We've got our analog mux right there. We also have our analog ports right there, ADC1. That's our A to D analog to digital converter right there. So we've got all types of things in these special function registers. And memorizing all these, I don't have them all memorized. I have to look them up as I use them. So there won't be any questions on the test where you have to memorize all these particular, all 256 of these right here, or 128. Well, there's 128 special function registers right there. We'll only use a handful of them in this class. Obviously, we're going to use port 0 and port 1, and maybe port 2. We'll use port 1 control mod and port 0 control registers. We'll possibly look at ADC that we'll be using the oscillator controls but we can control everything on this processor by writing to these special function registers. So everything, now your buddy's struggling up there. This room is warm. If I wasn't talking, I'd be dozing off. I got the advantage. I get to talk. You guys are forced to sit and listen. Of course, I can always sit down and make you guys come up and explain this to me. And So, okay. There's 8 modes of there. So you have to know all 8 modes right there. I just said you didn't have to know all the special function registers, but you do have to know the 8 modes of addressing. We'll do these in labs, by the way. We'll write labs where you have practice doing them. I don't expect them to memorize and look at this table. Although I find that if I say you have to memorize and give an example on the final exam, at least for the last semester, everybody just memorized the slide and just rewrote the slide to answer that question that there. But register to register, right there. Move B to A. I gave that example right there. We also have move a R0, for example. R0 is treated as a register move right there. R0 through R7. That's the advantage of using that there. Address, this is a memory location right there. If you see 30H like that, that means memory location 30 in the internal RAM right there. That's the internal RAM. If you see move X 30 hex A, that means, that's supposed to be a B, that means move A to 30 hex in the external memory. So the difference is when we put that X there. That tells it whether or not, and there's also a move C, only we can't write to that there. One of the things I didn't mention, let me just go back here, is this here is read-only memory during runtime, right there. During runtime, you cannot change the program memory. That's flash memory. The only time you can change that is when the tool stick is hooked up to the board and you download it from the PC. So you cannot write to this in your code, right there. This, when you're writing code, you cannot write to that. You can read it, but you can't write to it, right there. These here are read-write memory. You can write to them during your code. So the instruction move C 30X, comma A is not allowed. You cannot do that. That's a no. That there. You could do a move C A 30X right there. Because there I'm reading location 30X in the code memory and moving that to the accumulator. But I can't go the other way around. I can't write to the code that there. But we'll get into that in a little bit more detail. Indirect means that we place an address in one of the registers, and it's going to go to that register and get the address right there. So there's many times we will do that. If, for example, if we want to load a string, we'll load into one of the registers the start of the string, and then we'll read that data. We'll output it out the serial port. We'll increment that register, read the next byte into the accumulator, move that to the serial buffer, and then output that there. And we just go through and we write a short little program that just simply increments that till we reach the end of the string. We just send that out the serial port right there. If you see the number sign right there, that means that we're moving the data itself. That's actually going to move, we're actually going to add the number 80 hex to the accumulator and store the result in the accumulator. So whatever's in the accumulator, it's going to add 80 hex to it and keep the result in the store the result in the accumulator right there. The next set of instructions are for branching commands right there. There's 3 of those. There's a short jump where we jump within roughly 128 bytes plus or minus. There's an absolute where we jump within about 1K, and then there's the long where we jump anywhere within the code right there. So these are, so we got short jump, absolute jump, and long jump. And those commands sometimes get you, the short one gets you in trouble if you edit your code because it's relatively short right there. And then we've got move C. I talked about the move C command a few minutes ago. A, and then that's the address in the accumulator plus the program counter. And that one's used for various, like I said, string type functions where we put the start of the address in there, and then we add, I don't know why we would add the program counter. Oh. Right. Okay, the people going to talk to you. Oh, yeah, nothing important. Right there. So, okay, but those are the 8 modes of addressing right there. And again, before we start writing our code, we have to be aware of these 8 commands. This one we probably won't use that there. I'll probably do an example of it, but we probably won't use that many in our code. These we will use sparingly that there. We'll use those more for branching that there. Actually, there are some places we'll use that there. So the top 4 we'll use quite a bit right there. So, okay. This just kind of goes through, all these slides are just examples of what there's one slide, and I'll post these slides up on Facebook later today right there. So, but again, we're going to move the contents of the accumulator into R0. Remember, R0 is considered register addressing right there. And the advantage, again, of using the registers versus giving addresses is it makes our code much shorter. This actually happens to be a single opcode right there. Right there. So, right there. Whenever we use a register addressing, what the heck did I hit there to start my music playing? Right there. I should never pull my phone out in class, although I see a number of you guys do that from time to time, but not there. Okay, but the advantage of doing register addressing is that it is a single opcode, and it results in shorter programs. Now, we have a lot of code memory for the type of programs we're going to write in this class. A lot of code memory. 64K is a lot of code memory. Right there. In a real life project where you're controlling something that's complex, 64K may not be a lot of code. For this semester, it's a lot of code. I don't know if I told this class a story, but I think I did, about the guy who yelled at me for buying the PCs with 64K of RAM because no one could ever write a program that big. And of course, at that time, we were writing code in assembly language for the 8086, and we would never write a program 64K in any of our classes, not in assembly language. When you get into C or BASIC or any of the other high-level languages, it's fairly easy to blow through that 64K block. Matter of fact, our compiler that we've got, we're using the freeware Kyle compiler that Silicon Labs gives us for free. It's actually got a 4K limit on it, so we can't blow through the 64K because our compiler will puke on us before we do that. It'll give us an error saying exceeded that they're in. We want to write programs bigger than 64K or 4K. Go spend $4,000 and buy the commercial version of the compiler. So we're not going to write anything bigger than 4K because we don't have 4K USD to buy the full version of the compiler. That there. So regardless, but we want to keep our programs as short, because short also means as fast as possible. Right there. So direct addressing. This again. This is how we input data and output data. Actually, if we want to input and output data to our ports, we just do a move instruction. So this actually reads port 3 and puts the contents in the accumulator, right there. If we want to write something to port 3, we would do move port 3A, right there. Now our particular version of the compiler does not have port 3 on it, or the processor doesn't have port 3. Now, you should note that port 3 is a location in memory, right there. Port 3 happens to be B0, right there. Actually, B1, yeah, B0. This is B0, is port 3. So this command here actually is going to be replaced with, what did I say it was? I just looked at it right here. B0. This is actually going to be replaced with B0H, right there, is what that's going to, right there. So move into the contents of memory location B0H. But port 3 is what we normally would write, and the reason we can write port 3 is we include in all of our programs a header file that defines what the special function register names are, so we don't have to memorize the names and their locations. We don't have to memorize this table right there. If we didn't have the header file, we would have to memorize this table or look it up every time we want to use it. So this file here, Silicon Labs provides in order to make it simpler for us to write our code, where I look at this, and this simply, when I see the instruction move A, comma, P3, means that I want to read port 3 and put whatever is on port 3 into the accumulator. And port 3 is an 8-bit data port that can be tied to a series of switches, it can be tied to a series of, sensors, it can be tied to an external A to D, it can be tied to anything right there. So, right there. This happens to be below the contents of RAM location 20 hex into A, right there. So now we normally use A to do most of our input output. We don't have to, right there. Indirect addressing means that we place in R0 a memory location address, and we move A into that location. This is usually used if we're going to be using any type of array or string or something like that. We would use this type of address because we can increment R0 and then point to the next location. Increment R0, point to the next location. So we just load R0 initially, and we have a little loop where we increment R0 each time, and we grab the next location in memory right there. The data pointer, the transfer is pointed up there, should have a 16 up there. And notice that when I use the data pointer, I'm using the move X command. So the data pointer is a register inside the 8051, right there. Right there. Where is the data pointer shown? It should be here somewhere. E stack pointer, program status, workbook. Here's the data pointer right there. Right there. You see, and that goes to the external memory. The data pointer only works with the external memory, right there. So that is a register internally, and it can contain a 16-bit address. But the registers are only 8-bit. R0 through R7 are only 8-bit. But the internal data memory is only 256 bytes. It's only 8 bits address right there. The internal memory, I'll use that term internal memory, or the external memory can go from 0000. That has a 16-bit address. And as I warned you before this lecture, in comparison to C, this is a very tedious language to look at. There's a lot to remember. This is your first pass. You'll see a lot of this again and again. A lot of people wonder why I repeat the same material multiple times, because I have full faith in your ability to forget this after the first pass. And I'm rarely disappointed that even the best of students will not remember this whole lecture after the first pass. Actually, you won't remember most of it until you start writing code and download code into the board. And that's why I'm jumping into this here, so we can start doing some labs where you have to write some code right there. So, okay, but again, the data pointer is a 16-bit address. It's another register in the 8051. It's separate from R0 through R7. It's not contained in the internal data register. That's separate, part of the external memory interface right there. And it can only be used with the MoveX command right there. It's a very powerful tool because we can stick large arrays of data in our 4K external memory right there. That's on the chip. So if we're going to be working with a lot of data, we're going to probably stick it in that external memory spot, not use the 96 bytes we got available there. You got 96 bytes available on the chip internal memory. You've got 4,000 bytes available external. So where are you going to put it? You know, if you have a lot of data, where are you going to stick it? It's going to go externally, right there. So in this class, this semester, we probably won't use it we won't be writing programs that are going to be that complex. So we'll probably stick mostly with the internal memory. Our programs are going to be relatively short, right there. Matter of fact, probably 80% of our programs we can get by with the 8 registers in A and B. You know, just the 10 locations. But this is the indirect, right there. And again, this is very, very commonly used if we're going to be doing any kind of information with arrays or strings or things like that. When you took C, how did you learn strings? Did you declare it as a type string, or did you declare it as an array of char? Do you remember? You know, when you declared, let's say, did you do something like char 30 F name right there and declare it like this right here, where it's an array of characters that's 30 long, or did you do string F name? Which way did you learn how to do that, or do you remember? What's that, char? Okay. All right. Well, the reason I asked that is because that's the only way we can do it that there in assembly language. Because that's the way the computer is going to store a string, is they're going to store it as an array of characters. And each character is the ASCII code of that particular character in the string, right there. So strings are stored as an array of ASCII characters, is the way that they're stored. Immediate, you just simply put the data there. Add the number 30 hex to the accumulator, right there. Right there. Move the number FE00 right there into the 16-bit constant pointer register. This is moving that number, so that's actually an address in the external memory, is what that is. And we're actually moving that address into the data pointer at that point. That's how we initialize our data pointer, is with the instruction right there. So that would be this might be the start of an array right there. Now it might be fairly large. Now that's toward the top, so with that being toward the top, that's true external memory. Now some versions of the 8051 from Silicon Labs do have 64K of data memory external right there. They completely utilize that. The chip we're having does not use all 64K right there. So, but this is the constant. Everyone remembers the constant, but they forget to put the little star sign, number sign there. Because you've got 2 to remember. The at sign means indirect, that there means immediate, constant, right there. And nothing blank means the address. This means index. In other words, the address is contained there, and this means immediate. Right there. You have the 3 different things you have to remember. That if I put the at symbol here, R0, that means that it's going to be, the R0 contains the address of the data we want. The number sign means that we're going to actually add 30 hex to it. And if I just say R0 here, that means just whatever's in R0. So those are the easiest way to remember those 3 right there. Relative means right here, this is a fairly simple one. I decrement A, and if I do a jump, not 0, back to decrement A. So if A contains 200, decimal, that there means it's going to go around this circle 200 times, right there. This is how we generate loops, right there, and how we put in some time delays, right there. But notice here that we don't put the actual address there, we put a label. So when we use relative addresses, we're usually not going to put the actual address there. We're going to put a label, and a label is something right here that will, the linker, not the compiler, but the linker will replace this here in the code with the actual offset of where it's going to jump back to. That's going to be a negative number between negative 128, means I go back up 128 bytes or forward 127 bytes right there. So, but it's going to, when I do the jump not 0, go back, it's going to replace that with the actual physical address right there. So, again, we normally do it with conditional jumps, and we'll talk about the jump commands here later as we go through this right here. Absolute address, here we do an A call. A call means absolute call. This is how we call functions or subroutines, right there. You'll hear me use the two terms interchangeably. C only has functions. Other languages have subroutines, right there. But there's a difference. A subroutine doesn't return a variable, so typically these are more of subroutines versus being functions. A function in C almost always returns something unless you declare it as type void, right there. But A call port initialize. So this is going to call port initialize. Port initialize happens to be a subroutine in my code later on. Whenever I do a call, I will always end the subroutine with a RET for return, right there, in order to tell it to go back to where it's at. That there, we'll talk about subroutines in more detail, but this is just saying that this is going to be in the current 2-page of memory, right there. So, and then we have the long call. The long call is going to be a 3-byte instruction. The biggest difference, by the way, when we look at these relative addressing, when we look at the relative addressing, when we do the short jump, that's a 1-opcode command. The absolute is a 2-byte instruction. This one is a 3-byte instruction. We can do all long calls and our program will work perfectly fine. We never have to do a absolute. There's no reason we have to do an absolute, except for we're wasting a byte of program space whenever we do an absolute or a long one. We can get away with an absolute. So it has to do with saving memory space, is why we would do the absolute. The short calls are by default for the conditional jumps. Those are all, we can't do a conditional jump unless it's going to be a short call, a short jump right there. So a jump not 0, jump 0, those kinds of commands have to be short. If they have to be long, then we have to do a short jump to a long jump, right there. And that gets fairly tricky. We're going to avoid that right there. But and we won't have that problem in this semester. So, and index addressing is somewhat complex. In a lookup table, we have a 16-bit that there. We load the offset from the table start. We load the data that there, and we do a move. Now, notice here I said that could be had to be a move X. I lied to you. It could be a move C. Because in this particular case, we've stored a lookup table in our code data, and that's a good place to put in a lookup table. We stick it in our code data, and we move into the accumulator with the contents of A plus the data pointer from the code right there. So this is useful, for example, if I wanted to find the cosine of a value. And I don't want to put in the algorithm to calculate the cosine because it's relatively large. I load up a lookup table with between 0 and 360 the cosine of each of those 0 to 359, 360 is the same as 0, but we would load in that table with all the cosine values, and we would load into A the angle in degrees we want the cosine in, and we're going to then look up in our cosine table what the cosine is of A and put that in A. So this here actually looks up the cosine for us, assuming that we've loaded into our code data starting at this address all 360 values of the cosine. We have an easy way of calculating the cosine. We just look it up in a table, and we don't have to do a calculation, or the sine, or the tangent, or any other value that we want to look at. One of the things in the U.S., for example, is every state has a different state income or a state sales tax. Malaysia is simple; it's all 6% GST, right? The U.S. is a completely different bag of worms. Alaska has 0 sales tax. Indiana has 7%. California has 8.5%. Illinois has 7.5%. Every state has a different sales tax. Then every county within the state may have a county tax on top of that. So, and then some cities within that there. So, so if you're calculating the value of the tax, you had to look up the tax rate. You would have to you would load in all the tax rates for all the various counties within a particular state, and figure out what the tax rate is for that county. So again, the index is used mostly for lookup tables. That's what it's used mostly for. But those are the 8 different types of index up there. So I've got plenty of time up there. And again, we'll come back and I'll post these slides up there. Okay, we've got 5 functional groups on our instructions. So I'm going to give you, in the next 20 to 30 minutes, every instruction in the instruction set of the 8051. There isn't that many of them. That's there. So they fit into 5 different groups. So we went through the 8 different addressing schemes, now the 5 different types of instructions. The first one is the arithmetic. The arithmetic are simple. Here is all the arithmetic instructions. There's quite a few of them there, but they're mostly repeats of each other. This group here is all add, right here. And what they are is add with different addressing modes. Add ARN, that's using the register set. And RN is 0 through 7. R0 through R7. And B also counts as 1. Remember, B is also a register that we use. Right there. Add A, comma, direct, where we give it the address. Add A, at, and we give it RI, which is, again, the address is contained as the index address. And add A and immediate data. So we've got the add instruction. Again, it looks like a lot of various, but these are the 4 variations with the 4 acceptable that they're. We repeat the same ones with the add C. The add C is used for the carry flag, and we'll do it in a lab where we use the add C. The add C means we're going to subtract. We're going to add the carry flag to it. Right there. The carry flag is set when I want to add. I add 2 numbers and I overflow it. I set the carry flag. I add the next 2 digits. And then I add those 2 digits and add the carry flag to it. right there, because I carry right there. You know, if I add two numbers right there, I add 35 hex to 3E hex right there. 5 plus E, E is 14, right? So that's 19. So that's going to be a 3 with a carry, right? Well, this carry flag I have to handle. I can only add two 8-bit bytes together. So if I want to add these two numbers together, I have to add, and I'm just going to do add, you know, I'm just going to write a short little assembly language program to do this with just immediate data. Move into a number 5 hex, add to a number 0E hex right there. We have to put a 0 before a letter right there. And then I'm going to just move the R0A just to store that result right there. Then I'm going to do move into a number 3 hex. And then I'm going to add C, because I want to add the carry flag. When I added these two together, the result's going to be a 3, but it's going to set the carry flag. So when I do the C right there, that means add the carry flag a number 3 hex. So that's going to give me 7. If I don't do the C, this will give me a 6. So the add C takes into account the carry flag right there. That's what that does right there. And that's very important right there. So we've got those, that is for multi-byte addition. When I say multi-byte, if I want to add two 4-byte numbers that there, I would have to, that there. And notice that I had to store the result into one of the registers or someplace else. Whenever you write a program, you have to store the result someplace, right there. These again are the subtract. The subtract right there, subtract with borrow, you cannot, there is no subtraction without taking into account the borrow. And the borrow is similar to the carry flag right there. So if I have to borrow from a higher order, then I have to, right there. So I do the subtraction, lowest byte first, and we'll go through how we write code to add and subtract numbers of multiple bytes. You know, that's part of the labs we're going to be doing early on. It's just very simple adding, subtracting. We're not going to use the ports. We're just going to go through the single step and look at the contents of the registers and see that we get the result, right results. But we're going to write some labs up there. This group right here is our increment and decrement group, DEC. Those simply add or subtract 1 from whatever location we're pointing to. And again, we've got the registers, the A, the register, the direct, the indirect. We have the 4 addressing modes. So we got our increment and our decrement commands. Again, those are arithmetic instructions. You know, there's not a lot of instructions. Then we've got our multiply and divide. This does do integer multiplication and integer divide. Right there. And then we got our decimal adjust, which I'm going to kind of skip over. That does our BCD conversion, is what that's for, doing BCD conversions, right there. So those are all our arithmetic operations, right there. Logical, those are our AND, OR, XOR, or NOT. Those are they operate very similar to AND gates, OR gates, XOR gates, and NOT gates in digital, and they do it on a bit-by-bit basis. If I want to, so we have our AND right there with all of our various addressing modes right there. We have our OR with all of our addressing modes. We have our XOR with all of our addressing modes. We have clear, complement, rotate with carry, rotate, write with carry, these up there, and then we got the swap nibble. So these are all fairly straightforward. Out there. We will use those again out there. I don't expect you to memorize all these commands at this point. We'll use them in labs and you'll look them up out there. Not there. But if you write code, then you'll start learning. Right there. Not there. This is a short introduction right there. Data transfer, those are just the move instructions. Again, we've got our moves right there, move C's, our move X's. We got our push and pop, which I'll talk about later. That's dealing with our stack right there. And then we've got our exchange right there. Right there, exchange A. Those are kind of interesting because what that's going to do is it's just going to swap the data right there. And then we've got our exchange O or bytes right there, which we don't use very often right there. But in other words, exchange A with R, which basically is two commands right there. But it just allows us to swap whether there's an A with R0. It just swaps the two. It's a very useful command, by the way, when you got there. Especially if you want to say alphabetize a list and you want to swap. Normally you have to store that in a temporary location, and then that there. This just allows us to do a quick swap right there. So that there. So these are our data transfer. The ones that are most common are the moves, obviously. And we, believe it or not, probably 75% of our instructions are move instructions of some type. We spend a lot of time just moving data around. Right there. Our variable or Boolean, those are our clear bits. Clear C, clear bit. I actually said clear B. You don't need the B. CLR is defined as a bit operation. So if I do CLR P0.0, that clears that particular, puts a 0 to that port right there. If I do a set bit P0.0, that set writes a 1 to that bit right there. Right there. If I do a CPL port 0.0, that complements it. If it was a 0, it's now a 1. If it was a 1, it's now a 0 right there. So we could do a AND. These are bit instructions right there. We could move a bit to a particular, to carry a 1 or a 0. We could do this, and these are our single bit instructions. Jump if carry is set, jump if carry is not set. Jump if a particular bit is set right there. That one's kind of an interesting one because I could do a jump byte and I can say port 0.0 comma turn on AC right there. We'll assume that this is a location in memory that turns on the air conditioning in a room. Port 0.0 is coming from a temperature sensor through a comparator right there, and if the temperature is above a certain level, that bit's going to be high. So if that bit is high, I want to turn on the air conditioner. So I'm reading that particular input on port 0.0 saying that the room is hot. So I want to jump if the room is hot to turn on air conditioning right there. And I can do then a jump, and I'll call this start right here, back to start. And right here, I got a short little loop that's always just, all it's going to do is just sit there and wait for that input to go high and turn on the air conditioner. Now, you wouldn't write a program like that. That's, if you wanted to, if all you wanted to do is have the comparator turn on the air conditioner, then you would just turn on the air conditioner from the input. You wouldn't use a microcontroller for that. But this is just a short little example of where this set bit, and jump not set are used right there. Now, this particular one here is not normally used with a port, but an internal bit. We would jump, and that bit is set, and then we would clear that bit. So this might be a counter where we do a jump, and when the counter reaches a certain point, we set a bit high, we clear it, and then the counter adds up and counts it again right there. So, but these are our variant, and the big difference is that these are all operating on single bits right there. Right there. So these all operate on single bits. They don't look at bytes right there. So again, set bit right there. There's an example. Start timer 0. So that sets the bit TR0. You know, TR0 is a bit in the special function register. That there. And when we start looking at our special function registers, here's the timer, we'll see what TR0 is. It's actually buried in one of these right here, TR timer control right here. It's buried inside there. There's a bit inside that 8-bit register, you know, that 8-bit instruction. One of those bits is defined as TR0, right there. That's TCON is timer control. And that's a bit addressable special function register, right there. And then there's timer 2 control right there. So, but right there. Anytime you see see something that looks like right there where it says TR0, it's that bit TR0, that tells you that it's in that first column of special function registers, because those are all bit addressable. Here is poll, jump not bit TR0 poll. This is just waiting for TR0 to toggle. In other words, we started it here, and now we're waiting for it to overflow. Right there. And this is just a wait command right there. So this is a simple, we're using a timer, and we're setting a delay is what these 2 lines of code do. We start the timer, and we just sit around and wait for it to finish, and then we drop out right there. These are our branching. This is usually, I think this is our last set of slides here. That's our last set of slides right there. These are our call instructions and return instructions. We've got 2 calls, a call and a long call. A call means that it's within a 2-key range. It's, the subroutine is very close to it, the code memory. But their long call means we have no idea where it's at in code memory. Little note that I typically use the L call more than the A call, because as I edit code, what I sometimes happens to me is I've added enough code as I've edited my program that now my target is farther than the 2K and the A call won't work anymore. Fortunately, if that happens, the assembler will tell you. It will give you an error saying target out of bounds right there. And if you see a target out of bounds, it means you need to change from an A call to an L call right there. A return, RET, means it's going to return from a subroutine. Whenever you do a call, you push on, you don't do it, but the compiler or the assembler does it. It pushes on to the stack the return address of where the program is going to return back to when you did the return. Just like in C, if you called a function, when the function was completed, it went back to the same place, right? When you wrote a function in C, you did A is equal to, I'm just going to say X, Y, Z, A or B, C, right there. That's a function call, right? Somewhere down here, we had a function called int X, Y, Z, and it received int B, int C. They don't have to be ints. And then we would have our local variables. We'd have our function, right? Right there. And our function would end right there. And the last thing we would do is we would say X, Y, Z is equal to ... right? Right there. And so X, Y, Z, whatever we say there, is going to be put into A. Now this is not the accumulator, that's a C variable right there. Well, when this is translated to assembly language, a return is placed here. Because you got to remember, when you write C, the compiler translates that C code into assembly language, and then the linker translates that over into machine code. So it's a 2-part process right there. But you end up with a machine, well actually the assembler converts it to machine code. The linker fills in the missing addresses, is what it essentially does right there. It goes and it looks for the addresses for these A calls and these B calls and that there. It fills in all the missing addresses right there. But the compiler puts in a return right there, puts in the return. Well, we don't have a compiler, so we have to put our own return right there. So we would have, in assembly language, we would have a call XYZ right there. Blah, 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 blah. Somewhere down here we would have XYZ, and we would have some code right here, and our code would end with a return right there. So what would happen is when this A call is hit, it comes down, executes this code, it sees this return, and it's going to go back to right here. So that's what our return does right there. Now we've got another one here called return from interrupt. Now you have not ever heard of an interrupt yet, but an interrupt is something we'll talk about. But an interrupt is a condition in which the processor stops what it's doing and calls a particular subroutine. And we'll spend a lot of time talking about how interrupts work and how we set up the subroutines for when these interrupts are called. And because we don't know when an interrupt is going to occur, other things happen. You know, the registers are pushed onto the stack, the program counters push on the stack, the flags are pushed on the stack, and all those things have to be returned back to the original right there. So the interrupt, the return and the return from interrupt do similar things, but the return from interrupt does additional things right there. They're not interchangeable right there. The jumps, that there, we got 3 jumps, long jump, short jump. Those are unconditional jumps, they just jump. In C code, you were not taught how to do a jump command. In BASIC, they had a command called go to, and you would give a line number right there. In C, it's considered extremely, and C does have a way of doing jumps. You can set labels and do jumps in C, right there. But we don't teach that, and I don't even remember the command because it's such a forbidden thing to do in C, because it's considered sloppy programming to do it in a high-level language, that nobody teaches how to do it because it's considered such a bad habit that there. But in assembly language, we're forced to do it from time to time. Right there. So we have these short jumps right there. And then we also have jump directs right there, a jump direct right there. That one I don't use. Now, the next set of these right here, these are jump 0, not 0. These are compare and jump if not equal. These are decrement and jump if not 0. These are all used for looping instructions and conditional jumps right there. So that there. So in C, you have ways of doing jump, doing that there. But these are for like if then else structures or while structures, right there. So we would, and for example, you would do something like in C, you would do something like for I equals 0. I less than 10, I plus plus, right? Right there. And you would have some code in there. Well, you would use a register, and the end of this code would be a decrement or increment that they're in a compare, right there. So these are used for looping type instructions right there. Normally you try to normally you would count down, because it's easier to use a 0 than it is there. If you notice that all these are jump of 0 or not 0, you don't really have, here you have to do a compare and jump if not equal. That's what you would have to do that there. But we've got this decrement and jump not 0, which is actually a very easy command right there. So what we can do is we can use we could rewrite this instruction here for I equal 10, I equal 0, equal 0, I minus minus, right there. What we could do here to replace this is we would start this with saying R0 is equal to 10, right down here, and we would do a right there, decrement not 0, R. I left something out here. Right here, I would put a start loop right here. I need a label right there. That's what I forgot. Decrement and jump not 0. This is a D, not 0. R0, comma, S loop. Right there. And that does the same thing. It's just for loop right there. So this loads 10 into R0. This is the start. This is our start of our loop. This decrements R0, and if it's not 0, it goes back to the start of our loop right there. So this decrements R0 and jumps back there. So the first time through here, R0 is 10, then it's going to be 9. Next time through, it's going to be 8. Once R0 equals 0, then it's going to drop out of the loop and continue running. So that's how we would do loops in assembly language. Not quite as easy as C, right? Not quite as easy. Right there. So, with that said, that's our introduction to 8051 instructions. Everything from here on out, that there, and there, that will be, what we're going to be doing next is we're going to start learning how to write short little programs using this